Hello, geometry team, and welcome to Unit 11. We are beginning our unit on similarity in transformations. And I am Mrs. Cerna, ready to hit you with our day one stuff. And so to start off with, we're asking ourselves, what is a ratio? And this should be something you've already seen before in your math classes. A ratio is just a comparison of two or more quantities. And so it just explains how things are related to each other. And usually we do two at a time, but sometimes we can do more. So we can represent a ratio in a few ways. One way we can do it is just compare them side by side with a colon. A compares to B, or A to B. You could write it with words, A to B. A lot of times you're going to see ratios written as fractions, A over B, but it's still comparing just A compared to B, or A to B. And when you do any of these forms, remember that they can always be simplified. So whether it's running sideways or vertically, you can still simplify it. So, an example. You have a music store. You have 40 trumpets, 39 clarinets, 24 violins, 51 flutes, and 16 trombones. Woo! And it wants to write certain ratios in simplest form. So here it wants trumpets to violins. Whatever way you say it, that's the order you put it in your ratio. So for trumpets to violins, you're going to be putting, 40 trumpets to 24 violins. Now that is a perfectly acceptable ratio, but it is not simplified. So you would want to simplify that down, just the same way you would a fraction. Both of these are going to divide by 8, which would give me a ratio of 5 to 3. For flutes to clarinets, I'm going to write it in the fraction form this time. I've got 51 flutes to 39 clarinets. And so that would be my ratio there. But again, I always want to simplify my ratios. And so both of these can also divide by 3. And so this would simplify down to 17 to 13 for my ratio. For trombones to trumpets, trombones I have 16. I'm going to do it sideways again, 16 to 40. That can simplify down, both of these divide by 8. And so this could simplify down to the ratio 2 to 5. And for violins to total instruments, so I know that I have 24 violins. I don't know the total instruments. I'm going to have to calculate that. So sometimes that happens. Sometimes you have to do some work to find the numbers you need. And so I'm going to have to add up 40 and 39 and 24 and 51 and 16. And when I do that, that's going to come out to be 170 total instruments. So I have 24 to 170. Both of those are even. So when I simplify that down, I can divide them both by 2 and come out with the ratio 12 to 85. Okay, so that's ratios for me. Now, the nice thing is I can compare more than just 2. And so if I do a comparison of 3 or more quantities, this is going to be called an extended ratio because I'm going to compare 3 or more things at once. These ones are not going to be written as fractions because we don't do fractions with anything more than 2. Extended ratios are going to be written as first thing to second thing to third thing, A to B to C. Okay? And if we choose to simplify these, it has to be something that all 3 can simplify by at the same time. Okay? Now we use this when we are putting 2 or 3 or 4 things together very often. So an example, here I have a ratio of 2 complementary angles is 3 to 7. And I want to find the measure of both angles. Well, since I know they're in a ratio of 3 to 7, I know that 3 of the first angle and 7 of the second angle are going to be always going together to be complementary. I just don't know how big the degrees are. So what I'm going to do is I'm going to go 3 times whatever the first angle is, plus 7 times a certain number is going to give me, complementary means 90 degrees. Okay? And so some number 3 times plus some number 7 times, that puts that mystery number in our 3 to 7 ratio. And I know that these two numbers together add up to 90 degrees. So I'm going to simplify this now and get 10x is 90. And when I divide, I have a mystery number of 9. So now I can come back and find out how big both those angles are. So I can do 3 times my 9, and that's going to give me 27 as one of my angles. And then I can do 7 times my 9, and that's going to end up giving me 63 as my other angle. And you'll notice that this ratio right here, both of these divide by 9, simplifies down to a 3:7 ratio. So I used the fact that I knew the ratio was 3:7 and that that ratio added up to something to figure out how big they were. Using that same concept, here I have the ratio of two supplementary angles is 4:1. So that means there's some number that 4 of them gets compared to 1 of them. And that together, these two amounts is going to add up to supplementary is 180 degrees. So together, these add up to 180. So let's find both of these angles now. So this together, when I simplify it, becomes 5x equals 180. And when I divide that out, x comes out to be 36 degrees. Not 36 degrees, just the number 36. Mrs. Cerna, get your life together. So now I can go, okay, well, my two angles are in a 4:1 ratio. So 4 times this number will give me my first angle. And that came out to be 144. And then 1, I wrote the wrong color there, 1 of that same number will give me my other angle, which comes out to be 36. So the 144 and the 36 is in a ratio of 4:1. Okay? The ratio of the measures of the angles of a triangle is 479. Let's find the measures of the angles. Well, the thing you have to remember is here is the angles of a triangle always add to 180 degrees. So whatever size these angles are, they need to be in a 479 ratio, and they also have to add up to 180. So I'm going to have 4 times some number, plus 7 times some number, plus 9 times some number. Together, that keeps these all in this ratio, and then I know that they're supposed to add up to 180 degrees. So if I combine all of these together, that gives me 20x is 180. And when I divide it out, x comes out to be 9. So I'm going to use that 9 and say, okay, so I know that I had 9 to go into each part of my ratio. So I'm going to have 4 times the 9 for my first angle, 7 times the 9 for my second angle, and then 9 times the 9 for my third angle, so that each of these angles will still be in 479 ratio, just like we asked for. And so when I calculate this out, this comes out to be 36, 63, and 81 degrees for these angles. So now they're still in a 479 ratio, but now they all add up to 180. Once again, I'm going to do the angles in a triangle. I know those add to 180 degrees, but they need to be in an 11:5 ratio. So I need 11 of the first one, 2 of the second one, and 5 of the third one. And I don't know how big each of these angles are, but they should be in this ratio. And then I also know that together they add to 180. So I'm going to combine this out as 18x. And when I divide it off, x is 10. So now I can set up my ratio again. It's 11 to 2 to 5. But now each of them is going to get multiplied by 10, so that when I add them up, that makes 180. So this comes out to be 110 degrees. This comes out to be 20 degrees. This comes out to be 50. Now my question said, find the measure of the largest angle. Well, the largest angle was the one that had the biggest number on it, and it came out to be 110 degrees. These are more examples of the same thing. I will challenge you to do these to yourself. It uses the same concept where you have three numbers in ratio that add up to a certain number, you're going to work those the same way. Moving on, we're going to talk about proportion now. And so a proportion uses ratios. A proportion is an equation. And it's an equation that states that two ratios are going to be equal to each other. So if I have A to B is one ratio, and then C to D is another ratio, a proportion would say those two ratios are equal to each other. Okay, so that's a proportion. You have used these before. Well, algebra tells us I could multiply both sides by D, and I could multiply both sides by B, and I can do all sorts of stuff to simplify this. And in the end, there's something called the cross product property, which basically says if you multiply the numbers diagonally, the products you get from doing that will be equal. So if I do the B times the C, it is supposed to end up equaling the A times the D. And yes, you can prove that algebraically, but for now, you're going to trust me on that because you should have already learned doing this before. So if I have two ratios, I can use this concept, the cross product property, to find any one part of it that's missing. So I've got here a proportion. There are supposed to be 4 numbers in it. One of them is missing. If I'm only missing one number, I can always find that number. So let's work it out. I'm going to do my cross product here. So I'll know that 4 times 7 had better equal whatever 2 times x is. Well, if that's the case, then 28 is 2x. And when I divide out by the 2, x equals 14. And so 4 to 14 would equal 2 to 7, which makes sense because that's the simplified ratio of 4 to 14. Moving along, let's do a couple more examples. So I have a proportion that is missing one number, so I'm going to use my cross product property. 19 times the 12 right here is going to give me 228, and then 10 times the x will give me 10x. Dividing both sides by 10, x comes out to be 22.8. And yes, we can get decimals. We don't always get to live in happy whole number land anymore, so sometimes that's going to happen and the world will not end. Using this concept, we can get even more complicated. Here, I have a whole expression that's missing, but I can still use my cross product property. So I know that 19 times this x minus 1 going this way had better equal whatever 6 times 13 is. Well, 6 times 13 happens to be 78. Over here, I don't know what this is, so I'm going to just distribute it out and work with what I got. So this will be 19x minus 19. Well, now this just looks like a single linear equation. I can solve this. I can add 19 to both sides, and 19x will equal 97. So when I divide both sides by the 19, x comes out to be 5.1. So once again, don't always get whole numbers. The world doesn't end. Let's get even more complicated. Let's jump down to something with a negative sign. So here I have a proportion, 2 ratios that are equal. So I know that I can multiply the things diagonal from each other and they will be equal. So I'm going to have the 20 times the 2x minus 9 had better equal 10 times 9, which is 90. And so that's going to end up giving me 40x minus 180 is going to equal the 90. And so then let's solve for x. I'm going to add the 180 to both sides, bring it up here. So 40x equals 270. And when I divide off, x comes out to be 6.75. So that's using the cross product property more simply. Let's get it one step more complicated. Look, here I have 2 spaces in my proportion that are missing. I can still solve this using my cross products. I can multiply these 2 together, and I can multiply these 2 together. So before you panic, let's just try working it out. So I'm going to start here with 3 times the x minus 11 is going to equal the 18 times the x minus 20. Oh, that didn't look so bad. That comes out to be 3x minus 33. And on this side, I have 18x minus 360. So I can work with this now. I think I'm going to subtract the 3x from both sides. And that's going to give me, let's see, 15x minus 360 on this side. And over here I have negative 33. Let's keep solving. I'm going to add the 360 to both sides. And that's going to give me 15x equals 327. Now I divide off the 15, and x comes out to be 21.8. So still just doing the same old proportions I've done before. Now I just get to do a little bit more algebra to solve it. And you're thinking, wait a minute, this is supposed to be a geometry class. Why am I doing algebra? Patience, it's coming. Let's just do one more example before we go. So let's do this last one, number 19. Again, I have two ratios that are equal. I'm a proportion, so I can use my cross products. So I can multiply on the diagonals. So I'm going to do my 5 times 27 is going to, I should have put an equal sign in there. Mrs. Cerna, get a grip. Equals whatever x minus 1 times x plus 5 is. And so, boy, that algebra is really coming back in. So 5 times 27 is 135. And I'm going to have to multiply these out. You know, you can either multiply these using your box and do x minus 1 and x plus 5. Or you can FOIL and multiply, do your double distribution. I don't care how you solve it as long as you solve it. X squared minus 1x plus 5x minus 5. So when you work this out, you end up having x squared plus 4x minus 5. Still not done. So if you recall, when we get something like this, we need to put it into standard form. So I'm going to subtract that 135 from both sides so that it equals 0. And then I have x squared plus 4x minus 140. Now we know that when we had this kind of quadratic equation, it's a lot easier to solve if I can break it up into two things that were multiplied, kind of like it was in the beginning. But notice I have something different than what I had in the beginning, so I'm going to have to refactor this. And so when I factor this, I'm going to come here now to this pink box, and I'm going to start in the inside with x squared and minus 140 and figure out how am I going to split up that 4x. I'm going to need to find something that multiplies to negative 140 and adds to 4. And when I do that, I end up getting, let's see, 14 times negative 10 will be negative 140, and 14 minus 10 is 4. So these are my numbers. And so I'm going to have minus 10x minus 14x. And when I do my factoring for all of this, I end up getting x and minus 10 and 14. That's supposed to be a positive 14 there. Mrs. Cerna, get a grip. So I have x plus 14 and x minus 10 as my factors. And yes, this is the old algebra from the end of last year when COVID was happening and craziness. You're going to be okay. So I have the 0 property that I remember from last year that says if two things time to make 0, one of them better be 0. So if the x minus 10 equals to 0, that means the x had better equal 10. So that's one possible solution to this proportion. But wait, there's more. What if the x minus 14 was the thing that equaled 0? Well, then x could equal 14, and it would also work in that proportion. And so this one actually has two solutions. And that's okay. It's going to be fine. We can have that. Algebra allows for multiple solutions just like real life does. So why do we need to know how to do all this algebra? Now we're ready to use it. So now we're going to go into similar polygons and scale factors. This is going to use a lot of ratios and proportions. You're very excited, I can tell. Okay, so for similar polygons now, a similar polygon is a polygon with the same shape but different size. And we have mentioned things being similar before. And so we can tell things are similar without being told if we see certain things are true. The first thing that needs to be true is that corresponding angles have to be congruent. And so if all the angles that are corresponding are congruent to each other, that's my first sign that I have similar polygons. But wait, I also need a second thing to be true. I also need the corresponding sides to be proportional. And that's why we had to learn about proportions and ratios, is so that we have these proportions. And so the ratio of the corresponding sides, so when you compare any two corresponding sides of similar shapes, that ratio is going to be called the scale factor. And that should be sounding familiar because we just used that at the end of Unit 10 when we were comparing shapes. If polygons are similar then, you'll recall that if I have a linear scale factor, perimeter will also follow that same scale factor, so their perimeters will also be proportional. And so here, I'm going to give myself two similar shapes. These guys are similar. And so if I know they're similar, I can figure out the scale factor. What is the scale factor of triangle ABC to triangle DEF? Well, if they're similar, then I can pick any two corresponding sides. Oh, look, I can pick 14 to 21. And so since ABC was first, that's the number. I'm going to use the value I get from that triangle first. And so I'm going to say, okay, I'm going to use the 14. And I'm going to compare that to the 21 here. So the scale factor is going to be a ratio comparing parts of two of them, 14 to 21. But that simplifies. They both divide by 7. That simplifies to 2/3. That's going to work for any of these that I pick. I could have picked to use the 8 and compared it to the 12. If I make a ratio of 8 to 12, that's also going to simplify to 2/3. And if I do a ratio with 10 and 15, that also simplifies to 2/3. So my ratio of all my sides is always going to be the same, which is called my scale factor. Now, order matters. So here I did the scale factor of ABC to DEF. If I go backwards, if I want to know the scale factor going from DEF back to ABC, I have to write it in that order. So here I would do 21 to 14, and so that ratio is 3 to 2. Okay. Also, if I take the perimeter of these two right here, of DEF to ABC, the perimeters are also going to have the same ratio. So this perimeter, 8 and 14, is going to be 22 and 10. So this perimeter is 32. And this perimeter, 12 and 15, is 27 plus 21 is 48. If I take these perimeters and make their ratio, I want the DEF perimeter first. So it's 48. And my ABC perimeter is 32. That ratio also simplifies to 3 to 2. So the scale factors is the same for both their sides and for their perimeter, because they're both linear measurements, and so they have the same scale factor as long as the polygons are similar. Now, if you're going to write a similarity statement and say, yes, these triangles are similar, in order to do that, you must match the corresponding angles and sides, the same way we did with congruent shapes back at the beginning of the school year. So if I wanted to write the similarity statement for these two triangles, if I chose to say that the first one was triangle ABC, then I need to make sure I need to match up the similar angles and the similar sides. So if I start with A first, the one that is going to be congruent to it is D. So I need to start with D first. Then I have B next here, and so the one that matches up with it is E. And then I have C next on my first triangle, so I need to do F next on my second triangle. And then to say that they're similar, our similar symbol is this little squiggly tilde, like we used to see on top of the congruent sign. This is our similarity symbol, okay? And so that symbol is just this little guy right here. There he is. He's cute. And so, okay, let's use this and let's list all our congruent stuff in here. So I am told that triangle JKL is similar to triangle PMN. Okay, so I know these are similar. Now the order I wrote the letters in tells me which angles are similar to which angles. So angle J is going to be congruent to angle P. So angle J is congruent to angle P. Because if you remember, in similar shapes, the angles are the same size. It's the sides that are different sizes and stuff. And so my angles have to be congruent. So angle J has to be congruent to angle N. Then I have angle K with angle M. So angle K is going to be matched up with angle M. And notice they don't look like they're in the same position. This one must have been flipped around or something. But whatever it says in the letters, by golly, that's what goes in the picture. So here, angle K is congruent to angle M. And then lastly, angle L is congruent to angle N. So L is congruent. I had that all wrong, didn't I? I had J was supposed to be with P, and then I didn't mark J being with P. I marked it with N. This is why I need actual students around me to make sure I get it right. J was supposed to go with P, K went with M, and now L goes with N. See, I am going to get this right someday. There we go. So angle L is going to be congruent to angle N. I fixed it. All is well with the world. Everything matches up the way it's supposed to now. And so let's see what our sides are going to be. Now, our sides are going to be proportional. That means that the ratios are all supposed to be the same. So if I take side JK, it is supposed to be matched up with PM. So PM. That ratio is supposed to equal whatever other ratio I come up with. And so let's see, I've got K to L should go with M to N. So KL and M to N should be the same ratio as the other guys. And then lastly, if I have JL, that's this guy, it should be matched up with PN, and all of these different ratios should be equal, and so they are proportional. I can make a proportion out of them. So these are not the same size. When I compare JK to PM, it's not going to be the same size. However, JK and PM make a ratio, and that ratio should be equal to the ratio I get from KL and MN, and that ratio should be the same as JL and PN. So this one has equal ratios. These ones have congruent angles. Using what we see here now, let's look at this set of shapes. Now here, what are my two triangles? Well, one of them is embedded inside the other. So I have triangle XYZ, so that's X to Y to Z. So that's the big triangle, is similar to RYS. That's this smaller guy that's embedded inside it. and they are similar. So since they're similar, their corresponding angle should be congruent. So X should be congruent to R. So X and R should be congruent. Then Y should be congruent with Y. Oh, well, that makes sense because angle Y had always better be congruent to itself. Okay, that is our identity property, or anything is congruent to itself. And then lastly, I have Z being congruent to S. So S and Z are congruent because they are similar triangles. See, it said they were similar, so this all has to be true. Well, if they're similar, any proportions I make out of the sides also have to be equal. But the proportions, the ratios I make are going to be really interesting because I have to do, okay, so X, Y, Z. So how long is it from X to Y? Well, that's this distance, X to Y, and that's going to be matched up with R to Y. So that's this smaller one here. So X to Y is in ratio with R to Y. So XY and RY. Well, whatever ratio that is had better equal the length of YZ to YS. So YZ to YS. That's this big one here to this littler one here. So notice it's big to small, big to small. So on my last one then, I'm going to be doing a big, so XZ, to small, which will be RS. And so remember, I'm always putting this one first, then this one, and all these ratios are equal. They are proportional. Okay? Same thing here. I'm going to move past it for the interest of time and move down. How can we use this then to find measures? Well, just like we did at the end of Unit 10, these proportions and these scale factors here can help us find missing amounts. So here, I am told that these figures are similar with a scale factor of 2 to 3. And so remember, the one I say first goes with the one that I have first. And so here I have 2 goes with 3. And so then that means that this one gets compared to this one. So 42 gets compared to X. So this ratio and this ratio are the same. Well, I can now use that cross product to find the missing side on my figure. So I'm going to cross multiply here, and I'll have 2x equals 126. And when I divide that out, x comes out to be 63. So I know that this side is 63, which makes sense that 42 out of 63 would simplify back down into our scale factor of 2 to 3. Now looking at number 5 here. The figures below are similar, and they have a scale factor of 6 to 5. And so since I say the 6 first, this is the one I come across first, so it will go on top to match up with the 6. And then the 28 will go on bottom to match up with the 5. And since they're similar, I know these ratios are equal. It's proportional. So now I can do my cross product to find out my mystery side here. So 6 times 28 comes out to be 168, and 5 times x is 5x. So when I divide that out, x comes out to be 33.6, which no, is not a whole number. But 33.6 to 128 does simplify down to the ratio 6 to 5. Looking now at number 6, in these problems, I have this triangle ABC is similar to DEF. And so I know that their ratios should be proportional. So now I'm not given a scale factor. Instead, I just know that all the ratios I make should be equal. So I'm going to make a ratio with two sides that go together first. Let me make sure I pick sides that go together. So here I've got A to B. Well, AB should match up with DE. So yes, I did pick the right sides. So I'm going to put X in a ratio with 25 because they are corresponding sides. Well, I know that ratio should equal the ratio of any other pair of sides. So now I'm going to take BC, and BC should match up with EF. So when I make that ratio, the BC goes first, and then EF goes next. And these are equal ratios, so they're proportional. So I can use my cross product on them and get 20x equals 700. And when I divide off that 20, my mystery side comes out to be 35. And then number 7, we're going to use the same thing. Again, I don't know my scale factor, but it doesn't matter because all my ratios should be equal. So I need to find some parts that are corresponding. So it looks like I have PS and I have RS here. So let's see, RS would have to go with YZ. So I'm going to do RS to YZ. So that's going to be X to 32. Then I go, okay, PS, which piece should PS go to? Well, P connected to S, so Z should connect to W. So that's going to be this piece. So that means I'm going to take the 75 and put it with the 40. Remember, this one is always going to come before this one in my ratio. Always do the same side first. And so this sets up my ratio. And now I'm going to cross product. So I'll have 40x equals 2400. And when I divide both sides by 40, x comes out to be 60. So I was able to use the fact that they're similar to figure out the length of the missing part. Moving on in your packet, there's several more examples, okay, where I can do this. So let's look at number 8. I've got triangle DEF is similar to triangle HJG. And now I need to find two different sides. So again, all my sides are going to be the same ratio to each other, so I can set any pair equal to any other pair. So if I'm looking for X, that's segment GH. Well, G and H are connecting those two parts. Well, that means that F and D should be connecting. So if I connect F and D, these two pink ones are the ones that I'm going to put in a ratio because they're corresponding parts. So I'm going to put X with my 12. Okay. Actually, I put that backwards. I want to do DEF first. The one I say first here is the one I want to put first here. I like to keep things consistent. And so I know that 12 should go with X. So 12 goes to X. Well, then I need something else on this first triangle to go with something else on my second triangle. Now, the only thing I know on my second triangle is this 15. So now I need to find its corresponding part over on my first triangle. Well, this is J connecting H. When J connects with H, that's the same as D connecting with E. So this is my corresponding part here. So with my 15 on my second triangle, I should put 9 on my first triangle. So 12 goes with X and the 9 goes with the 15. When I do my cross product, that's going to give me 9x equals 180, and X comes out to be 20. So I know that X is 20 here. Well, now I'm going to keep going. Now I want to find me that Y. Well, Y is going to be going with the 14. So I know that I have 14 going with Y. Well, I can pick any other ratio I want, any other set of sides in ratio that I want to go with it. So 14 is going with Y. So I can put, say, the 9 with the 15. And that ratio should be the same, no matter what. So let's set this one up now. That's going to give me 9y equals 210. Divide them both by 9, and y equals 23.3. So once again, we get to leave happy whole number land. Here's where the good times start. Now I have shapes that are crisscrossing this way. I say that they are similar, and I need to find values of x and y. So again, you need to want to match up corresponding parts. So if I want to find x on my big triangle, that's going to be connecting K and L. So if I'm connecting K and L on my first triangle, I need to be connecting M and L on my second triangle. So that's actually this guy here. So x is going to go with the 14. So now I need to connect two other pieces, and I need to connect two that I have their values for. So J to L would go with N to L, but oh look, I don't have that Y, so I can't use it because that would mean I'd have two things I didn't know in my proportion. I don't know how to do that. So now I'm going to go, okay, well that means that JK goes with MN, and I do know both of those numbers. So I will use these numbers in my proportion here, so I know that 40 goes to 16. And now I can cross product that, and 40 times 14, and I'm going to have to multiply this out. So let's see. 40 times the 14 comes out to be 560 equals 16x. And when I divide it out, x comes out to be 35. All right. And then I go, okay, now what? I found that x equaled 35, and I'm changing it to pink so I can put it here in pink. I don't know why I switched it to green. So now I need to find my y. Well, y gets put in ratio with 45. So if I put the y with 45, well, I started with my small triangle here. Oh no. But the nice thing is that ratios work whether they're upside down or not, as long as you keep corresponding stuff together. So if I do small first in my ratio, I need to do small first in my second ratio. So if I did y to 45, I can do the 16 to the 40. So I can use my fractions upside down as long as I'm still keeping parts in their corresponding positions. And so I have 40y is going to equal 720. And when I divide it out, y comes out to be 18. All righty. The same thing is going to set up for these other three, so I'm not going to work the rest of these examples. However, in the hard copy of notes, you will see those examples worked out if you want to see how they go. Thank you very much, team, and have a great day.